Hi everyone, and welcome to this session, which is going to focus on a simple pendulum in the same way that we focused on the mass spring system in the last session, where we are going to see how those general formulas we came up with a couple of sessions ago then relate to the specific issues around the simple pendulum. As always, it's really important to remember what simple harmonic motion is. So it's motion where an object is oscillating such that the acceleration of the system, which is acting to restore it to equilibrium, is directly proportional to and in the opposite direction to the displacement from equilibrium. So I know we've said it many times before, we're going to keep saying it because it's really, really important to define. So important just to remind ourselves of the equations while they're on the formula sheet, just understanding the relationship. So displacement of the system in terms of time is a cos function, which is there. Velocity and acceleration can both be expressed in terms of time and trig functions as well, but are more usually expressed in terms of displacement. So velocity with the more complex equation in the middle there, and acceleration with that defining equation equal to minus omega squared x. And then we've got our usual frequency equations, which are useful and will pop up a little bit later on. Okay, this was from the very first session on simple harmonic motion, so I'm not going to run through the whole derivation of this again. Remember, it's not examinable anyway, but we're just looking in terms of the forces acting on a simple pendulum system. And the key thing is this bit down at the bottom again, where the acceleration for a simple pendulum was given by minus g over Lx, and that verified the simple harmonic motion because g and L both constant for the pendulum. So again, it was acceleration directly proportional, but in the opposite direction to displacement. But the key thing here is how that relates to our general equation, similar to what we did with the mass spring system. Always worth just ensuring that we know what assumptions have been made. The measurement of the length of the pendulum is key, that it is from the point of suspension to the center of mass of the pendulum bob. The key thing with that is that is not just the length of the string, and it's not just the length from the top to the bottom, it's to the center of mass. So that's something really to consider going forward. The string being light and inextensible and remains taut throughout the motion. Okay, so taut, therefore we're not changing the not losing any tension in the string throughout that. It's remaining that way all the way through. Otherwise, it won't be following this. It'll be following projectile motion. The string being light, so we're assuming that it has no mass. Light being very specific in physics to say no mass. If it does have a mass, then that's obviously going to change the center of mass and the effective length of the pendulum, so it becomes more complex. It's still manageable as a question, but it does need a little bit more thought. And inextensible, as in it's not going to change length as the tension varies throughout the cycle, because essentially this is in, as well as being in simple harmonic motion, it's prescribing a vertical circular path. It doesn't complete the circle, but it does prescribe a circular path, and therefore the tension will vary throughout that path, which would, if it was extensible, if it was able to extend, would of course change the length of the pendulum as well. So we're assuming that any extension is negligible. So in an ideal situation, inextensible. And as we discussed when we did those early derivations, we're going to be looking at small angles. The maths relies on small angle approximations, so we need to make sure that we abide by that. So as with the spring mass system, we can look at the general equation for simple harmonic motion and relate it to the specific equation that we've got for a pendulum in terms of acceleration and displacement. And you can see straight away from that G over L is equal to the angular frequency squared. So same format as we had for the spring mass system, just different constants this time. And as we go through, so that rearranges just to be angular frequency being root G over L, and change that to periodic frequency, so 2 pi f equals root G over L. Quick rearrangement, and then inverting it so that it's time period instead of frequency yields this one, which again is on the formula sheet. Its time period equals 2 pi root L over G. And just like we analysed last time with the spring mass system, you can see there's only two things that the time period depends on. Different things this time. It's the length and the gravitational field strength. So no dependence on the mass of the pendulum bob. Bob is a technical term, by the way, for the mass on the end of a pendulum. So no dependence on that this time. That actually cancelled out in the derivation. Does depend on the length, but no dependence again on amplitude for exactly the same reasons we discussed last week. If it's a higher amplitude, yes, it's got further to travel, but there's also therefore higher accelerations, which yields a higher average speed, which keeps the time constant. And under most circumstances, gravitational field is constant in this as well. So the only thing that affects really the time period of a pendulum under normal conditions is its length. And actually you can then conduct an investigation changing the length of pendulums to actually determine the gravitational field on Earth. And that will be part of your required practical. You might also notice, it's just worth highlighting, it's not exactly the same, but it's a very similar format, particularly if you look at the frequency equation at the bottom left. It takes a very similar format to the equation that you will have had for the first harmonic in stationary waves. And actually, there's a little bit of tweaking to get the dimensions quite right there. But it's worth pointing out at this point that they're similar, and the reason they're similar is because a particle oscillating on a stationary wave actually also follows simple harmonic motion. So there's an application there where there could be crossover between stationary wave studies and simple harmonic motion. Have a little look at a worked example then. Okay, so a clockmaker wants to build a grandfather clock with a pendulum that swings with a frequency of 1 Hertz. How long must the pendulum be? Okay, naturally we're making the assumption that he's going to build this pendulum on Earth as well. So again, it's just a case of putting numbers into an equation really and just being careful with units and rearrangements. It's more of a maths issue here than a physics bit to answer these particular mathsy examples. So first thing is we're given a frequency, not a time period. Now it's quite easy this time because we're given a frequency of 1 Hertz, which just yields a time period of 1 second. But just be careful, you'll be quite often given frequencies instead of time periods and have to do that little conversion. And then we're going to use our new equation. And rearranging for that, therefore, we're trying to find the length. So a quick rearrangement of that, we've had to square the whole equation and rearrange it so that it's in terms of L, and it gives us L equals G T squared over 4 pi squared. And then it's just being careful with those squareds in particular. I'm putting the numbers in, so 9.81 times by 1 squared over 4 pi squared gives us a length of a pendulum of 0.25 meters. And then remembering that that's not the length of the string, that is the length from the point of suspension to the center of mass. That's absolutely key. Right, so just to finish off, as with the spring mass system, the last thing to consider is you will do a required practical on pendulums as well. It's all actually both things contribute to a single required practical. You have to study the spring mass system and pendulums together to complete one practical. So it's two elements to a single plan. For this one, what we're going to ask for is that you describe a method that would test the relationship between the time period of a pendulum and its length. So straightforward in that you can think of what you actually need to do to change the length of a pendulum and measure its time period. But as with last week, we've got to be considering the equipment that we're going to use, again, specifics on the measuring equipment, and then consider how you're going to reduce uncertainty in this. Okay, what practical steps are you going to take so that you reduce the uncertainty in your measurement? And then the key thing, and this is, like I say, this is a good way to verify the acceleration due to gravity, state how you could determine the acceleration due to gravity from the results that you collect for this. And also you would be expected to say how your results verify that this is undergoing simple harmonic motion. Okay, so reasonably straightforward, very similar things to last week, just a slightly different equation to end up with, and just a few extra points, particularly in the assumptions to consider with regards to pendulums. Okay, all the best. Bye.